I am the general chair of this conference since the first conference. So I just like to thank all our organizing committees, our general chairs, also our long-time supporter, Dr. Samir Khan, who has been with us for a few years already. And then all our keynote speakers, thanks for coming. All our industry speakers, especially applied AI track this year. We have a lot of applied AI track speaks too, right? And thanks for all our volunteers here also. Let's get started. Our first talk is Dr. Dilma da Silva, sorry. The topic is scaling system software. Welcome.
Good morning, everyone, and thank you so much for the invitation and for the opportunity to see this conference. I really enjoy when we have a lot of sessions from industry, so I really appreciate it. Let me tell you a little bit about me so you can see if you're going to believe or not on the things I'm presenting to you. So I'm a professor at Texas A&M currently, and since July, I am on this rotation, meaning that the federal government borrowed me from the university, and I am at the National Science Foundation in the Computing and Communication Foundation, part of NSF. But my academic career is a little unusual because I joined Texas A&M from industry. So I joined as a department head without ever being a professor in the United States. So you can see that they took a risk, and I did too. It was fun. Everything worked out. I knew the most important thing was faculty have no bosses. They were not going to read my email. So it was very different from my time in industry where people actually read my email. So, but knowing that, everything worked out really great. In industry, I spent 12 years at IBM, and then almost 3 years at Qualcomm Research. So the story is that when I decided to move, after my PhD and sometime as a faculty in Brazil to industry research, I went to IBM and I had a lot of fun there. Eventually, I got curious about how Silicon Valley worked. So, and I also got curious about smaller systems. At IBM, I was working very large scale systems, from supercomputers to, really large data center things. So I thought, okay, let me work a little bit on the other side, and that I did for a while, and decided it was time to go back to academia. So I think one interesting aspect of looking back, we usually, give talks about the results that we generated last month, and we're eager to talk. And I have some of those, although I have to confess that this morning I received the decline from SOSP. This is a system of a symposium of operating system principles. It's a prestigious operating system conference, and I just got a decline, so I'm a little like, okay. That result, I'm glad I'm not presenting because it seems people don't like it yet. But if you look really back, when I joined IBM, it was to work on a new operating system, which sounds really weird. Who wants to work on operating systems? If you look at the years 98, IBM was starting to embrace Linux, to really embrace Linux at the time. But at the time, Linux and all the other operating systems didn't scale for even 4 processors. Right? At the time, we're not talking cores and things like that. We used to say processors, right? So if you put a workload, the workload people used to use was, let's compile the Linux kernel. That was a common workload. And if you now put it in a machine that instead of 1 processor has 4 processors, it took much less time, much more time. Why? Because the whole kernel had 1 lock. It was called the big kernel lock. So the thing was not scalable. Everyone knew that. And we, this group at IBM said, well, we are going to design a new operating system. It will be scaled, from the ground up to be scalable. Okay, but I would like to share with you that we also thought that Microsoft Windows would totally dominate the market. So as we, more academic, Unix people, were doing this, let's say, invested a lot of time on having a dual personality operating system. It offered both the Linux API, ABI, and the Windows API at the time. So that was a prediction that we had. It didn't pan out. A lot of things that we also thought, yes, shared memory, multiprocessors, lots of, you have a question already? Oh, thank you. And I will try to figure that out. So let me see. I go to Zoom, and then I can see it to click some window. Where should be that click?
Yeah. The second screen.
So maybe if we leave my window, my PowerPoint, this will be able to see it, maybe? You can? Oh, you got it. I can see it. Okay, very good. This, okay.
Is it good?
I think it is. Okay, thank you. And thank you so much. Otherwise, I'll be like half an hour and then everyone will be embarrassed to tell me. And I don't embarrass myself very easily. So, okay, so, but we, like some people said, yes, large shared memory, multiprocessor is increasingly important. There was a convenient belief for IBM because, for example, the machine I had in my lab at the time had 32 processors. Not a lot of people had those machines, but this took a while, and you really had to have a lot of money to invest in hardware at that time. So it was not like we could bring a lot of academic partners. And we also believe that's okay, because 5 years from now, every laptop will be multi-core. And yeah, our cell phones are now very multi-core, but did not happen in 2003. So again, if we wanted more people to work with us on our systems, we had to donate the machine. Our toolchain was also for PowerPC processor. What at the beginning sounded like a good, not a bad thing, because you may recall that Apple sold their Mac servers, they were Power. So, okay, there is a low end, it's just one core, but there is a low end. People can do software development, and soon things changed. You may recall that Apple was very nimble in moving all their tool chain from PowerPC to Intel. And then boom, now even to compile our system, you needed a PowerPC machine. And at the time probably started at, I don't know, 20K, right? So this was not really look good. I'm not trying to make you feel bad for us. This was, you know, how things become. We also thought that we were going to do object-oriented. So we're still talking about when people thought C++ was too slow for anything useful. We don't believe that anymore. We're doing a lot of very useful things with much more overhead in languages. But at that time, we thought, yes, we're going to pay the overhead, but it will really be great because objection structure will really help us. And then we also thought that let's go 64 bits because that's the future. Again, not a bad prediction, but if you think about it, in the Intel, in the x86 world, what you had was Itanium coming up, and Itanium was not a success. And therefore, again, this was a full IBM thing. So this is really hard to make it happen. So yes, we should have had a 32-bit version. We never had. And we totally missed on virtualization. So look at the years again, 98. So 98 is when the professors from Stanford, Rosenblum and his teams, they were publishing on hosting multiple operating systems on the same platform. Their papers were about getting fault tolerance for things like supercomputers, but on the side, of course, they were porting their stuff to real hardware and they were founding VMware. But we, IBM had a hypervisor already for the mainframe and for the PowerPC, but we just didn't see the connection. That was only hold us. And the object-oriented design and infrastructure that we thought would be so cool for customizing, you want a new memory manager, you want a new scheduler, you just extend your class with a subclass. became so complex that our interns would just come, and by the time that they really understood the base of the code, it was time for them to leave, for example, right? So it didn't work out very well, but we did a lot of things. And because IBM also was really embracing Linux, the mandate of this project became demonstrate ideas to scale Linux, demonstrate on this, port to Linux, and convince the community if the ideas are good or not. And we did that for scheduling, for memory management, for file systems. Some things they totally didn't like it. Other things they liked the idea, re-implemented, and other things like, I guess, our tracing infrastructure, they really adopted. So it was a learning experience on scaling software. We're not thinking cloud yet. We were thinking large machines that were running big workloads. That's what we were thinking. Once virtualization came up, I remember that a lot of senior VPs would call me and like in 20 minutes, tell me what this is and what is the difference between Zen and KVM, that kind of discussions, right? But it was a refreshing moment for operating system people. I think we forget about that because it gave you a way of doing something different. So operating system people, you have Windows and Linux, and they're big and they're very hard to change. But you now could have this thing on the side. Maybe you could explore library OSs, which actually people have done. And through virtualization, I believe there was, at the time, I thought, wow, this is like a once in a lifetime moment of seeing this disruption that you can try everything out now differently in the design. Well, now when I think about disruption, I'm thinking about other, all this data-driven disruption that all of us are thinking about, how our systems will go. So as disruption goes, this was quite small. But it was a momentum to really think that, yes, you have to live with legacy software because you have all the software all over your companies, our places have, but maybe virtualization can give you a little on the side. And so we did explore and had projects on virtualization. We explored a lot of memory over commitment through virtualization, things like that. And we had one project that was large. It was, a very senior vice president or president, whatever, a very senior person at IBM, a small distance from the CEO, wanted to demonstrate that you could put 500 blades, that blades were the big thing at that time, and really manage them well and run workloads, enterprise workloads. So we worked on that, and on that we leveraged virtualization so that we could have, general purpose operating systems, Linux running, but also our own lightweight operating system that would be accelerating at the time WebSphere workloads, which were important for IBM. We also worked with the DB2 people in order to help them with cluster support. This is when Oracle and I guess IBM, they were competing on having those, now instead of buy one box, big box for a database, you buy a cluster. And therefore we were working on that. So this was also a lot of experience in finding shortcuts within the operating system, within the runtime libraries to accelerate the workload for people. And we actually got very good results. You probably would not be surprised that we in the research division got results that were good enough to keep us alive, meaning the senior management giving us money to continue the project. But on the next step would be for some product to really embrace the code base. We didn't succeed in finding one. They thought it would be really complex and expensive to maintain. So it died at that point. So there are a lot of patents. We generated a huge number of patents from this, but ended up not really being critical for business. As this is going, look at the years 2006, 7, 8. You already had across the globe, I believe, in all companies, someone coming up with the cloud. At IBM Corporation, I probably know 100 people who say that they brought the cloud idea to IBM. I'm not one of them. I had people in my group who were really paying attention and telling, look, you can really make money with this, offering of renting Linux virtual machines at 8 cents an hour, which was the price on the first release. It was not an easy sell to everyone. I guess if we look at the business at the time, business magazines, a lot of leaders were concerned that cloud would only work if you were in a company like Amazon that supposedly had all this spare capacity that were there for Thanksgiving, Christmas workloads for selling. And the rest of the year, they had to keep it any way they could get money on it. But, a lot of people across all companies, I'm sure, certainly at IBM Research, we did a lot of analytical models. We kind of like proving that there was a business model. And we went ahead, myself and a few people, and we built a cloud for research the customers would be the 2,500 people who are in the IBM research part of the corporation. And so we built it. And after, we built it in a couple of months, kind of like, not very different from AWS, but, offering our machines. And after 6 months, we had 600 users, which was a huge success at the time. Now feels like a joke, but and we had 2,000 virtual machines instances per month. Again, I got a paper published at a good place about it. People were really excited about it, and we got a lot of visibility in the company. And the challenge, of course, is that this was being done with researchers, and there is a culture fit, right? So some researchers love to do product because people are using their stuff, but some of them, they want to do the first design, and as soon as there is a bug report, they prefer someone else handles it. So there was a little culture problem. There was also a culture problem regarding, for example, the chargeback functionality. The head of research, who is a senior VP, among like the top 5 that reports to the CEO, he heard about this, and he called me and he said, I want a chargeback functionality in a month, meaning he wanted blue money being charged. This is all blue money, not that it was money, but should be that people are receiving the bill. And I wanted this in a month, otherwise, I will, I shouldn't say that, but let's say that it will not be good. If anyway, so I decided I was going to implement it because they wouldn't fire me at the time. It's just like, I was quite sure I wouldn't be fired at the time. And therefore I did implement the chargeback functionality. And it was probably the last time I wrote any production code, meaning any code that other people use, but not me or my students. But I could also, again, see this thing. So we had all this working. And of course, by now, IBM is building a business on it. And then it becomes that they use the software from researchers, or do we build everything using their system management tools? IBM a long time ago had bought Tivoli, a company that did system management. So they had this rich thing. And we lost the battle. People decided to implement with Tivoli. And kind of like, so we partitioned, and then what my team started to do was the connection with the open source, and we created a benchmark that was adopted by the SPAC organization. So that's what we did to help Tivoli. We were not really, helping it. And that was until 2010 or so. And then I moved on to another project at IBM. And afterwards, they did leave behind this Tivoli implementation and redid it from the scratch. So that was kind of like, so what is the learning thing here for all of us? I think in particular, if we have here graduate students, they're very attached to their own ideas and their own code. And I do think a good lesson learned is just, let it go and sometimes embrace other things. And it's, but also be able to really capture what is new from your things and articulate to other people in a way they can use at least the ideas. And I think that my time scaling software on those projects, I didn't tell you that I was also, managing part of the Blue Gene software group. Blue Gene is like this supercomputer that IBM was doing. There was the LP, Q. When they were doing Q, I was not there, but L and Q. And also, it is quite different to do for the supercomputer. For example, we had a totally reliable network. It's very different to write software if you know that every message is going to arrive in order by guarantee of the hardware, right? So this is another kind of scaling that we also did. Then when I moved to Qualcomm in 2012, my day job when I was working when I was in the Qualcomm Research Lab in Silicon Valley, Santa Clara, explicitly. And then, I would go to a lot of meetings in the corporate headquarters in San Diego, and they would refer to me as the cloud lady. So all this cloud thing was totally not on the radar for Qualcomm. And I learned it is a great company, but not a company that made money on software. So I came very spoiled from IBM because when I was working scalability was important for IBM. So people, they really would, even people own the business people, they would appreciate, they want to hear me. When I was then trying to tell them, let's look at cloud, again, I was really appreciated. And the virtualization was appreciated. My life was so easy, I didn't know. Then I go to a wonderful company that makes a lot of money from the intellectual property on the design of chips for cellular networks. And then when I tried to sell or any idea with software, they only remember everything they tried and they lost money. And they only remember how much money they spend maintaining the tons and tons of Android software stacks for the companies that they do chips. So it is a different thing. So, when you are a software person and people I had a little bit of that experience once, when I interviewed at GE. So GE was becoming a digital, they were like in the very first thing, we're going to become a digital company. And they really asked me to interview. When I went to interview, I interviewed with the head of trains and motors, and they were not keen on having a digital company at the time. They did, as we all know, did a very good, incursion into digital. So I had that interview where, I learned a lot, but let's say it was not the most pleasant. I knew I was not going to get a job offer, and I also knew I was not going to accept a job offer if it came. But at Qualcomm, the thing is that I did a lot of things. Intellectual property was really good. So I did a lot of things I can't to this day to talk about, but I did something I can talk about that it relates to scaling. I was participating at a smaller contributor, meaning I was not a key person in the team, this 12 people team, where they wanted to scale, use better multi-cores on the processors to run games. So we wanted a library that you could put below the usual, your favorite libraries for doing games. And if it was a Qualcomm chip, boom, it was going to be running better with less battery consumption. So this was really a parallel computing project. So, and that's why when I, could see this project, I said, oh, I can contribute to that. I know a few things about doing parallel programming. And but it was interesting that they did manage to get that in the product, even on this environment, this skeptical value of software. I think one project I had that people really liked was about optimizing compilers. We had one like that I had 5 people working, and that one I think people really was not skeptical. But this one, they were reasonably skeptical, but not that much because it was being ported to products. And the challenge and where things didn't work out well is that, and you probably know better than me, at least at that time, it was really hard to keep talent in Silicon Valley. The way I describe it in my mind is that these colleagues that work with me on Sunday have brunch with their friends from their undergrad, from their masters, from their PhD, and they learn about, other companies, and they all get on this, oh, am I sitting too long in a company? Should I move? And every Monday then I had to be the psychologist of all these people, trying to convince them that sometimes staying in the same place so you can say you really delivered something makes sense. I thought that if you jump every 3 years, 20 years later, I am not sure what narrative you could have if they did care. Maybe people didn't care. But anyway, so I had a lot of people working on indoor localization for me, and then one-on-one, all this. And they were doing something that the client was Google, and one-on-one, all of them went to Google. And for this group also, the group went being absorbed. So that was the hard thing. But I did like to remind people that the kind of thing that you learn in a traditional academic environment, and all the papers you read, when you had a chance to actually do this, this is also really, really gold. So if you think about all these projects that I mentioned, or this field that I mentioned, they are all resource management. And you could say that many of us here, that, some people that I know their work, what they do is what memory and what CPU and what network and what storage goes to which application and what time. Essentially, is the resource management problem. And the problems are not solved. I would say that, of course, the problems that we had with the clouds in the very beginning was like placement, where I put my VM, how I pack the VMs, do I put IO bounded workloads, memory intensive on the same or not? All those conversations, I think that companies solved, and the academia with the companies, I think, explored. But it's not like they're totally solved, because right now, where we put my serverless functional invocation and how I do the scheduling. So it is, again, a revisiting of all of that. And it is in some way hard, because the problems were not solved, but a lot of things they succeeded. And we have to think what we revisit from the past. And for people who submit papers from academia, from any student who may be attending, it is always hard, because it does seem that people always criticize your paper, like, oh, this paper from 82 or 96, tried that didn't work. And that always existed. I remember when we interviewed people at IBM Research, I had one particular colleague that anyone who interviewed, the person would say, we tried that in 73, does not work. And therefore, we just prepared the candidate not to be, offended, and to try to actually learn and see what was going on. So it is really okay. And we now have so many software stack that is hard to innovate. We have to work it. And many people are now saying that it's really harder to do this kind of research in academia because you don't have the workloads. You do not have even, traces that you could use to do. And that is true. Anyway, so after 2014, I did move to academia, as I mentioned to you, and then an interesting thing that is hard for academics to think is that, like in the if I had changed my job at IBM to a very different thing, you just clean your inbox, right? It's like, and this for me was similar, because I certainly could not work on anything that I was really working at Qualcomm. It was just clear They continue to file the patents on things I was doing. They would not even tell me that the patent was being filed. But of course, they'll put my name because, you know, I was involved in the discussion and the ideas. But you do have to restart with a fresh stack. And I think that it is really good. So it doesn't happen to academics very often. Every now and then people do change the areas radically, but also they do, you know, have to see what the students want to do and things like that. Initially, I was working with colleagues who had an idea, an algorithm for something on a data center, but they didn't know the problem. So I was like, oh, I heard a lot of problems, so let me find the problem for your solution. And I did work that was fine. Eventually, I decided to work on stream processing, meaning having those systems that you receive new data and query all the time. Stream processing, it had academically an app for a few years, and people were designing languages, and then that didn't really go much. And then it was not that hot, but then eventually what happened is that, you know, with 5G and Internet of Things, this idea of data coming all the time, and we're trying to derive some understanding or deriving some view of the current state that could be using for data-driven decision-making. Here, I'm not talking inference or anything like the traditional, this is the state of the world, and I do whatever I want to process on this. This became more important. It was beyond having a computing paradigm. It did introduce different ways of looking at applications and cluster management. System management is an interesting thing because for a while it was considered, oh, people who, you know, will manage your Linux box in the network, not very, let's say, prestigious in terms of research. Then in the 90s, there was some time that people were trying to do some system management. And then I guess with cloud, with the provider having to solve the system management at large scale, this was not that precluded. But so about the streaming computing itself, funny enough, I heard about it at IBM, but it was a secret project for a while. So there was the secret project. I think some people like it's Voldemort, or, you know, this is Harry Potter days or whatever. So I don't want to say that was exactly the nickname, or if that was us who were out of that project, how we refer to the project. But from that project later came IBM System S, was an IBM system for streaming. When it was a secret, it was because it had a specifically agency from the United States government that was sponsoring for, you know, specific things. And again, if you look at the time, 2001, the world really became the surveillance may be relevant because you want to learn about possible attacks before they happen. So anyway, a lot of things happened. In 2008, there was this particular hardware and software that was with a language just for this streaming. But also you could look at Yahoo, and they had a streaming system that they published. And you could see, you know, others coming from the open source people like Kafka. And then you'd look like Twitter had Apache Storm and Apache Hero that not only were open source, you know, Apache projects, but also were published at a prestigious data management conference, SIGMOD. And interesting enough, if you look at those papers, and you want to say why they had Storm and they went to Heron, is because they wanted to have more processing, more parallelism, and they also wanted to have more data arriving. So when you increased the parallelism and the data, the blue line, the one that is not scaling very well, is their first system, Storm. Then their new version, Heron, they published to say, look, we changed the internal design, and now when we throw more data and we throw more processing, it goes well. right? So it was scaling. On the other graph, instead of looking of how much you can process per unit of time, we are looking at the latency between receiving the data and having that data impacting the result. So, the classic, what are the most popular Twitter hashtags right now, right? So like all these tweets are coming and you want to keep the top 10 or whatever updated. And what is the latency? And the latency, we could see with the storm, more than 1 second between data arriving and data being accounted for in the whatever summary they were creating. But with Herald, they were able to make it in less than half a second. So, and a lot of groups, academics, and from industry continue on those years to come up with other systems for streaming and also publishing about that. So very large databases, I think that's what VLDB stands for. It is a prestigious database conference. And in 2017, you had 2 papers about streaming systems, and one of them from LinkedIn. I think from LinkedIn, what they said that the Twitter solution didn't really work is because they wanted to integrate with events from an enterprise system. So it was not just receive the data and give me some sort of a summary. It was receive the data and act on by sending things, and where you receive the data also, they really needed to be events from the other systems. So they open source SAMSA. And beyond open sources, you could read the papers and see Facebook had quite a few. So for example, one that offer you a SQL-like language. So if you know how to do queries on databases, they're traditional databases, you could not write the same kind of query for this data that is coming up. So it's a lot of things that are happening because and a lot of companies, if you look at each one of those projects, their page where they listed the companies that use them, the list is very long. Of course, companies are so big that what does it say if it says Apple or Amazon uses, if they use in a small corner project or if they use as a key component, that doesn't become clear, but they were doing that. So when I get to work on this, what am I going to do? Like, again, a lot of things have gone done. So we decided to work with, now that you make decision making, but you keep some state into the nodes. So that was the angle that we took. So introducing stateful streaming. And at the time that we started this in 2017 was not crowded place. So I said, oh, people are not doing that. So we could focus on doing state recovery, very distributed, using a lot of things people learned from distributed hash tables, things people have been doing to scale software, we applied to this, and we also want to be able to tolerate a large number of failures at the same time. And it is one of those pieces of work that the individual ideas have been published before. People have been, they were working about, stragglers. If you had, in your system, not all machines in your cloud are the same. Some of them are smaller. So the MapReduce people have worked on a lot of those problems with the stragglers, but they could be really bad here. And we're trying to get the best pieces and put together. And we wrote a couple of papers about it. And, I'm sure you're not interested in all those details, but the idea is that you could apply those distributed ideas for stateful streaming. And then we took it a step further and we made it so that could be very customizable. It would learn how the network was. It was learning and adapt to the system. So that's another thing that many of us have done, and I have done many of my projects. At the time, it was, you just notice and adapt. This link is low, so you put things here and there. You have more of those autonomic computing things, which was for a while, autonomic computing was a thing. So some, people would like me remember we had conference. We still have a conference in autonomic computing, and it's still a good conference. But that what we brought that customization. And I think one thing that we were not very lazy is on the evaluation. So we would evaluation when you had 500 nodes and you have like 50 simultaneous failures. So I would say that this line of work, we spent a lot of time doing evaluations that were not too toy evaluations. Like sometimes we start with toy evaluations, all of us, but we did it much more. And then more recently, we said, okay, stream computing is important, but now it is on the edge, and the edge, maybe this idea that, for a while we all got so excited and we were centralizing in the cloud. And of course, it didn't take long for people to say, well, for certain things, we need to bring them closer to the edge, that decentralization with a low network cost is not good. But I would also like to showcase that's not an easy idea to sell. Professor Satya from CMU, who is, has all accolades of being very successful, having done a lot of fundamental work in distributed systems and mobile computing, around 2010, he started submitting papers, what he called the cloudlets. And I was reviewing those papers on the committees. And then I could also see the technical reports on his webpage, which were the papers not accepted yet. And I have to say that I was sad to see he couldn't sell his story of this cloudlets. And he tried to say, there's no more network for disaster recovery, so it's good to have cloud in the edge. People did not buy. A lot of things people did not buy. You can look, it's an interesting thing, we don't like to tell graduate students about failure so that they don't give up on us, and much less assistant professors or professors, but it is an interesting thing. Of course, he was already a full professor, super successful, who had also founded very successful companies. So for him, that failure, was not a big deal. It's for his students don't like the rejection. But he got a paper then published on that idea, and the use case was, do you guys remember when Google Glasses were really popular? Okay, if you're around with your Google Glasses in your neighborhood, there are kids from your neighbors that are walking around, those images, people would believe that image should not go to the cloud. So the use case that he used was for privacy. So again, it took 4 years, I think, for his first paper, but he's acknowledged as one of the creators of this idea of cloudlet, fog computing, edge computing, and then of course a lot of people were starting that. But it's an example. When I was at Qualcomm, also of course I was the cloud lady. So I was the edge cloud lady, because if you think about Qualcomm and cellular networks and their relationship with providers, the idea that you took traffic out of the network, can you see for Qualcomm and their Verizon, AT&T, it is something that, they want to hear, but it was really hard to have a real use case, and I did talk to a lot of companies, and including once that the CEO of Facebook at the time, Meta, and the CEO of Qualcomm met, and they were like, oh, this edge thing should be fun, put the people to do it. And even when it came with this blessing from above, the challenge is that what's the killer application really that you can't right now go? So the killer for company, and that was not there in 2012. Some people believe that the clear application will be the kind of application that will allow me to be living by myself when I'm 80, so 10 years from now, so get your work done, so that the house is helping me. Dilma, the milk goes on the fridge, not on the closet, and the house is telling my doctors how much I'm moving. I think people think that all on that space of privacy, a lot of costly computing, a lot of data with a lot of training methods, that may be a killer application to Edge. And I really, I think I could say, I worked with, the people who distributed NFL content, all kinds of people trying to find the killer application in 2012, 13. That was hard. And I think if I would do now, I think people here who work on Edge, you can make your case right now. And one case that people are talking, of course, is autonomous vehicles, for example. I think I even have a picture. That's the one that we did in our paper. And naive or optimistic that I am, so I'll tell you, I had at the time, right now I'm in NSF, I have nothing. But when I was a professor, I had a project with the Department of Transportation. It was a sizable project for academia, $7 million. This is for the deployment of autonomous vehicles in rural areas, and evaluate the technology. How are those cars going to work in farms and rural areas, right? So I have the cars, I have the data, I can now really do real experimentation. And of course, with COVID and other things, the cars are still not getting data. That has been 2 or 3 years, it's slow. But so we didn't use the data from real cars, but the idea of having edge processing for this, we did propose a design, and we showed that our design, you can deploy a large number of applications at the same time. And we did better than the other academic things that have been published until then. And also we handled failure up to a large number. So we showed that we could scale the design that we proposed for streaming running on edges. And that's what we worked. And like a lot of people are working on serverless computing, but as I just told you, I submitted many papers. I think we have something cool, but so far it hasn't been published. So maybe next time, I can tell you about it. I've already talked for more than 50 minutes, I think. So I think it's a good time to take questions if you have any. Oh, thank you. Thank you. Very kind of you. Yes.
What would be an example of a stream processing?
Thank you for that.
What would be an example of a stream processing engine on the edge? Like recently Spark came up with, Spark.
Yes, Spark.
Spark came up with its engine on the mobile. Would that be an example where you would use stream processing on the edge?
We were thinking more about shared infrastructure in a city where people would deploy different applications, from parking garages to interactions with the cars that are coming around. So we're really thinking that people would have several applications that would make sense in a particular corner of a particular city, and that there is data being from all those sensors from the city, and the applications would come on those data sets and decide what they wanted. So it could be marketing applications, could be, all kinds of those. So those, and what kind of hardware? We're actually thinking reasonably powerful hardware, the kind that the companies that sell hardware now, they sell or they brand it as edge server. So that was that. So the Internet of Things, and as you said, the mobile devices integrated like something like Spark. It is an alternative model. It's an alternative model, but Spark there are other. I think Spark has a version for streaming more recent now, right? And they the challenge now is like, if you go very optimized, you probably can do streaming better. But if you can leverage the overall let's say, buy-in of a given platform could be better. So I myself may end up saying you should use this version of Spark and not our system. It really depends.
Thank you.
Yeah.
So thank you, great presentation. You gave several examples, especially when you were in industry, of really good research sort of losing, if you will, to business priorities or business clashes. Any guidance on how to avoid those clashes, or perhaps how to,
And maybe there was also the momentum that was happening with the industry labs. So, places like IBM Research and Microsoft Research and other places, I would say, could be considered a little spoiled in certain parts of their lifetime, in the sense that they were bringing this, let's say, brand and prestigious. They don't really have to show the return of investments. Then, with crises like the one in 2008, it became very clear that if you're not advancing the corporation should cut you, because the corporation needs to respond to their obligations to the stakeholders and everything, right? So there's nothing that special. What is special maybe about research is that the hiring is not as fast as in other areas, and having someone who has been there for a long time and saw many waves, like experience, may count a little more than certain other projects. So that was the momentum. And I think that the model, the way that I like to encourage current graduate students, meaning people who are getting a PhD because they want to continue to do innovation, is do not look at your title if you're in the research or in the development part of the company. Try to see, is this an innovation in the sense that it's trying to solve a really hard problem? So, and maybe I am a little more flexible than most professors or most researchers in that sense. I do think that if you're trying, even if it's short term or medium term, if you're trying to really solve a hard problem and thinking medium term, you may not be able, like us, we did something for 6 months or 1 month. We didn't take that to cloud, but that was not wasted, because the people who stayed there, they had a critical, they became what they call like the IBM fellows, and they were promoted, and they were recognized for thinking about the problem in a more in-depth, from the scratch way, even though now the implementation is not like that. So I do think that it is a matter of a little bit how people manage their individual careers to make sure that they expose them to innovation and challenges, and make their own career choices a little more long-term. And you can do that even at IBM Research at that time. If you wanted to have the highest salary increase and the biggest bonus, you did have to be working on something that was really benefiting a customer. You do that, you are on the SWAT team that they send to solve a problem, you're going to get the biggest bonuses, and you're going to get the biggest thing. But you may also decide that long term, I want to do something else, so I will be okay with my modest bonus and my modest salary increase. No one was, everyone is reasonably compensated. Therefore, I saw that the individual also making choices in that environment. So I don't know if I addressed your question, but it is a good thing to think for all of us, because I do believe that now research is really in all companies. It's just that I guess I would say I'm not working in a company right now, but I would say that this is a year where long-term ideas may not be well received right now. So work with reality, right? Work with reality. Yeah. And so we have the 2 questions here then.
I'll go first. Since I got
Yeah, then okay, you got the mic. Yeah.
Thank you, great presentation.
Thank you.
From your vantage point and observation, what do you think when do you think the economics is going to play out from a practical industry adoption point of view for the extreme aspects of the edge computing one?
So for the edge computing, and I'm really bad on prognostics and things like that. So one reason that I moved to academia is that I had no idea where the stocks were for any company that I was, just not me. And also I didn't want to have my own company. But I do think it is the time to get, if I were working at a company right now, I would say this is the time to try to get mindset or trying to get your framework or your approach to do, because I think a lot of applications will come. Probably on the short term, a lot of applications that are really good at inference, some training, some federated learning, all of that. And I myself would probably look for applications that are not that one, because a lot of people are working on that one. Like I would like to see, other applications that may benefit from a different combination of hardware and software services than what we need for decision-make, data-driven computing that leverages deep learning or leverages reinforcement learning or large language models or whatever it is that they leverage. So I don't know when it'll be, but I would invest my, if I had a group, if I were still at IBM, I would probably try to really do the business case and convince someone to let me have a group working on it. Yeah.
Hi, thanks for a great talk. I'm just curious your thoughts on something. When you think about the complexity of managing infrastructure, like you mentioned, with cloud systems and cloudlets and Docker and Kubernetes and stuff, what I saw is like software-defined networking came out as a solution to help scale up the management, which was causing a lot of problems in networking. And I'm curious, what are you seeing that would be the similar kind of thing for basic computing infrastructure management?
So I think that the ideas from software-defined network, we all saw the soft computing. What was that? The soft storage net. We had all those terms. And I do think that it's hard for me to think right now because the space is so taken with how we can have the system learning from itself and make better decisions. I think there's so much focus on that that I'm more concerned. Is this the thing that we are putting components that then they will not be able to adapt or so that's where but I don't have an opinion. I decided myself not to work on machine learning for systems, but I do read all those papers and trying to see where it goes. And I think it would be even much more complex than software-defined network was for networking. And maybe because I drink the Kool-Aid of the software-defined networking. I'm now at National Science Foundation, and we are so proud that we were the ones first funding research in that area. And therefore, we see it as a success. But I do think that the system management problem, in particular causality and really being able to do the code auditing that we may need to do in the cars, anyone who followed, you remember Toyota cars where supposedly all these old ladies were pressing the accelerator by mistake and they were dying. And eventually, it was shown that that was a problem with the thing getting stuck, right? If we look at the level of auditing that they did in order to understand what was happening, I keep thinking how they're going to do now with the more complex transportation systems, not only cars, but hospitals and everything. So how we're going to do this problem determination. And yeah. So there's a lot of problems. Thank you. We know we are over time, and I really appreciated you listening to me. It's a pleasure to be here. Thank you.
Sorry about it. We need to put this petition on, so we need to give it some time to release. Thank you so much for the talk, and a few announcements. Everybody should get 2 drink tickets. That's very important. If you don't get drink tickets, go to the registration desk and get tickets. That's it. And we're going to speak during now.